So if we know the formula, then we can get some insight into its chemical reactivity. Well, one of the tools we've been using is to figure out the charge on the atom. To figure out the charge on the atom, these are oxidation numbers or oxidation states. And so we've been doing that already. Like, for example, what's the charge on manganese here if it's MnO2? MnO2 would be plus, no, oxygen's -2, so plus 4. Yeah. And so we're going to formalize that procedure into this. It's a summary of the oxidation number assignment rules. This is the one from your book. There's also one in the supplement, and there's one that's in Chem 1A, which is a little different than this. But the rules go like this. The oxidation number of each atom in any elemental substance is 0. So if you have an element in elemental form, all the atoms are going to be 0 charge, like H2. Each atom in H2 is 0 charge. He, 0 charge, etc. So if it's an element in elemental form, it's 0. The oxidation number of monatomic ions is the same thing as the charge. So if it's sodium +1, what is the charge? Is +1. Magnesium +2, the charge is +2. N3-, the charge is -3. That's monatomic. So the oxidation number of combined oxygen is -2. So normally we do oxygen first. I erased it, but oxygen at -2. And so we figured out for manganese. Here, sodium oxide, oxygen would be -2, each sodium is +1. Magnesium oxide, oxygen's -2, magnesium is +2. I don't write it like this. I don't say equals. MgO equals -2. That's not right. The charge on oxygen in MgO is -2. So I don't like exactly how this is presented, but the exception is peroxides. Peroxides, oxygen's -1. If you try to make hydrogen peroxide with -2 oxygen, then you get an impossible charge for hydrogen. So if we look at hydrogen peroxide, we have H2O2. We have 2 oxides. That can't work because each hydrogen would have to be 2+ to balance out the charge. This whole thing is neutral. But the problem is hydrogen only has 1 electron. Can it lose 2? No, it can't lose 2 because it doesn't have 2 electrons. You know. And so hydrogen peroxide, the oxygen has to be -1. And the same thing in other peroxide. There's superoxides too. I really haven't talked about superoxides. Superoxides are O2 -1. So superoxides O2 -1, which means that the average charge on each oxygen is -1/2. -1/2. And so somebody asked me about fractionals, but there's ways of thinking about the fractional charge to make it make sense. Because can you have a half of an electron? No, you can't. And so the fractional charge, we'll talk more about this later. And so that's superoxide. But this is later because this is chapter 19. So chapter 19 relies on a little bit of the earlier stuff. So I'm eliminating some of the stuff so it doesn't rely on the earlier stuff. Then we have OF2. OF2 here, which one wants the negative charge more, fluorine or oxygen? Fluorine wants the negative more, or electrons more, or oxygen wants? Which one's a more powerful oxidizer, fluorine or oxygen? Fluorine's more powerful. Fluorine's the most powerful. And so if there's a competition for electrons, fluorine versus oxygen, who would win? Fluorine would win. And so in this case, fluorine wins, oxygen loses. So oxygen ends up with a +2 charge in this, which is unusual, but it's not that happy. But fluorine would be terribly unhappy if it didn't. Hydrogen is +1, except for hydride. And the sum of the oxidation states has to equal the net charge. You know, if the net charge is 0, the net charge. So basically, we've been using these rules all along, figuring out the charge. So there's some practice in here that needs to be done. And so this will give us a little bit of insight into its redox properties, but there's some stuff I need to finish from chapter 7, which I haven't finished yet, I think. And that is, what else can we get from the composition? When we look at the composition, like H2O, H2O, this is what I get in terms of oxidation states. Hydrogen at +1, oxygen -2. This gives me some clues. Like, for example, what do you think? One, I make an association. H2O, stable or unstable? Stable. And therefore, these oxidation states are okay. So +1 on hydrogen is okay, -2 on oxygen is okay. In fact, oxygen wants 2 electrons anyway. And so these are happy as is, you know, versus a -2 on some other species might not be happy as is. So what we do is we make an association with, you know, some factual observations about water, it's stable, and then associate with oxidation states. And so I see oxidation state. Well, where do we get these? We get this from the composition. Now, there are different ways of representing the composition. The composition is represented by a formula, is what we call an atom or mole ratio. And so for water, we have 2 H atoms for every H2O molecule, for every 1 H2O molecule. And so it's an atom ratio like that. We have 1 oxygen, etc., for every H2O. We have 2 hydrogens for every oxygen atom. Or it could be a mole ratio. That is, we could have 2 moles of hydrogen atoms for every 1 mole of H2O molecules. When I say mole ratio, I'm talking about a counting unit. It could be a dozen ratio, so 2 dozen hydrogen atoms for every 1 dozen water molecules. And so this mole ratio is just the number ratio. Atom ratio is just the number ratio. So atom or mole ratio is what we got. So when I look at a formula like this is 2 atoms of hydrogen for every 1 atom of oxygen. Or 2 dozen hydrogen atoms, 1 dozen oxygen. Or 2 moles of hydrogen, 1 mole of oxygen. Well, the convenient thing about moles is because of the mass relationship. The mass relationship, we had 2 masses that we usually care about, the molecular or atomic mass. And so, for example, water consists of, actually let's do H2O. We got 2 hydrogens, hydrogen's 101. We got 1 oxygen, which is 1600. So H2O is 18.02. Now, we have molecular atomic mass, we have molar mass. And so the only difference is the units. If I'm dealing with molecular atomic mass, this is 18.02 U per molecule, per H2O molecule. Now, that's a single molecule, but if I had a mole of these molecules, then it would be 18.02 what? Grams per mole of H2O molecule. And so this numerical relationship comes about by the definition of the mole and the definition of the U. So it works out nicely like this. And therefore, this is what we commonly do. We commonly do this. So if I had 1.00 grams of H2O, one of the first things I want to do is I want to get that into moles of H2O. The reason is because once I have it in moles of H2O, then I can use these mole ratios like this to figure out other things. Because, or atoms, or molecules. The reason is because the formula is the atom or mole ratio. It's not the mass ratio. And so let's look at the composition by mass. So this is one of the most common conversions that we do, is a gram to mole conversion. Why do we do that? It's because of the way we write the composition. We write the composition in terms of this. But if we're doing composition by mass, the formula would look totally different. And so if I want the percent of A, then that's going to be the mass of A over the total mass times 100%. And so if I want the percent hydrogen in water, the percent hydrogen is the mass of hydrogen. The mass of hydrogen will be 2 times, I'm going to go 1.08 this time to get 4 sig figs, divided by the total mass. What's the total mass? 18.02 times 100%. And so this could either be in grams per mole or U. It doesn't matter. So I'm not even going to write the units for this. And so that's going to be 2.016 over 18.02 times 100%. And so what is the percent hydrogen in water? So 2.016 divided by 18.02 is 11.187. 11.187. We're allowed 4 sig figs here, percent hydrogen, H. Well, there are only 2 components, so if it's 11.18, then the percent oxygen is the rest of it. And so the percent oxygen I can do in 2 ways. One, I could just do 100% minus 11.187%, which gives me 88.812% oxygen. Or 2, I could just do the mass of oxygen, which is 16.00 divided by the total mass, 18.02 times 100%, which is going to give you the same number here. So if I were to write this formula in terms of a mass ratio versus an atom ratio, it'd look like this. I'd have H 11.187, O 88.812. Now I could leave it in grams. If I just left this in terms of mass ratio, then I could leave it in grams, and then I could figure out how many grams of hydrogen or whatever else. But we don't leave it in mass ratios. Formulas are not mass ratios. Formulas are atom or mole ratios. And so we don't represent formulas like this. This is not a formula. This is a formula, H2O. In H2O, we have not the mass percentage, we can get the atom or mole percentage. And so this is 2/3 hydrogen. 2/3 hydrogen is going to be 67% hydrogen, 1/3 oxygen. 1 out of the 3 atoms is oxygen, so there's 33% oxygen. We can get more sig figs here if we want. But in terms of, this would be percent by atom or mole. So by atom or mole versus a percent by mass, like this. Okay, so that means this. If we want to do quantity relationships, then we're going to have to usually do a gram to mole conversion. So let's do an example calculation. 1.00 grams of H2O has how many H2O molecules? And so normally we do a calculation like this. We start off with 1.00 grams of H2O, and then we'll convert it into moles. Turns out a mole of H2O molecules weighs 18.02 grams. A mole of H2O. And so the grams of H2O cancel. That leaves us with moles of H2O molecules. And then I know how much a mole of H2O molecules weighs. 1 mole of H2O molecules weighs 18.02. Oh, actually, I'd be going backwards there. What else do I know about moles? Well, 1 mole of H2O molecules has how many H2O molecules? Yeah. And so 1 mole of H2O molecules contains 6.022 times 10 to the 23rd molecule. And so this will give me the number of molecules to how many 3, 6, 8. All right, how many H atoms? If I want to figure out how many hydrogen atoms are present, then I can do the same thing. I would go 1.00 grams of H2O, and then I'd convert it to moles of H2O by inverting the molar mass here. So that takes us to moles, and then from moles I'll go to moles of hydrogen. And so for every 1 mole of water, there are 2 moles of hydrogen. So 2 moles, 1 mole of H2O. And then for every mole, I know I have an Avogadro's number's worth. So 1 mole of H will contain 6.022 times 10 to the 23rd H atoms. Mole. And so this will give me the. And so these are typical calculations that we do. So from the formula, we can do quantity relationships like this. From the formula, we can figure out some of the chemical properties. And so the formula is very important for us. And so how our formula is determined, let me talk about that next. Turn this on. How our formula is determined, in other words, how is the composition determined? So knowing the composition is going to give me a lot of insight into how it behaves, in other words, its properties. And so if I have a liquid here, how do I know what the composition of this liquid is? Well, the first thing is that liquid a mixture or pure? It's a mixture. If it's a mixture, then we have to do some separation, isolation, and purification. Figure out each component of the mixture. And so what we do is we just separate it into different substances, pure substances. Once we have it into different pure substances, then we want to know what is the composition of each of those pure substances. And so to identify the composition, of each component, well, now if we have pure components, we can measure its properties. And compare to known compounds / elements. You know, if it's pure, it's either got to be a compound or an element. And so here, what I do is I isolate it, purify it, and then I measure something like the boiling point. If I measure the boiling point and it comes out to 100, then is this pure water? It must be H2O then, correct? Could there be something else that boils at 100? There could be. So what you want to do is you want to make absolutely sure by measuring additional properties. Measure as many properties as you can and then compare it. And then when we have a match, so for example, did it boil at 100? Did it freeze at a 0? You know, is it fairly unreactive? You know, does it, like, say, for example, if I put if I put sodium in here, it's going to react. But is it fairly unreactive, et cetera, et cetera? So we go through this. You know, what is its pH, this type of thing. And then once we've measured enough properties and we compared it, then we can be pretty certain, hey, the composition is this because it matches. The properties match. But what if you don't have a database of properties? What if it's a new compound? Let's say you're trying to synthesize something new. If you're trying to synthesize something new, then there are no properties to compare it against. And so if it's unknown, totally unknown, then what we do is we can just send it out for chemical analysis. There are actually lots of different techniques of chemical analysis. One of the techniques is, for example, elemental analysis. Elemental analysis is you can ask them to test for certain elements. So let's say you suspect that this is some hydrogen-oxygen containing compound. What you can do is you can send it out for analysis, and they'll figure out how much hydrogen, how much oxygen is in the sample. They won't tell you if it's pure or a mixture or whatnot. They'll just tell you how much of each is in there. So you got to make sure it's pure before you send it out. And so this will give you a breakdown of what elements there are and what the amounts are. This is difficult though because it's expensive, and you have to have an idea of what it is, so that you don't test everything in the periodic table, which would be one, it's not possible, and two, it's even testing a limited number gets expensive. There are more specialized techniques like sulfate analysis. Rather than looking for specific elements, we look for specific ions. So how much sulfate is present in the sample? Sulfate, sulfides, fluoride, how much fluoride is present in the sample, etc. And so we can analyze for specific species like this. All right, so basically what you're going to get back from chemical analysis is this. The results of chemical analysis are usually a percent by mass breakdown. So let's say we sent out a sample for chemical analysis, and the sample came back as 74.1% carbon. So they analyzed this, and they got 74.1% carbon, 8.64% hydrogen, and 17.3% nitrogen. And so this is the composition, but this composition is by mass. It's not by atom. And so it's not like 74 atoms of carbon, 9 atoms of hydrogen, and 17 atoms of nitrogen. Because the atoms weigh different amounts. And so what we want is, we don't want the mass ratio. This is the mass ratio. What we want is the atom ratio. And so how do we get from the mass ratio to the atom ratio? Well, you know, I'm sure the chemical analysis companies can do it, but they'll charge you, and it's so easy to do, we don't bother having them calculate it for us. What we do here is we just do some math. The first step is we're going to assume we have 100 grams. If we have 100 grams, then it's 74.1 grams of carbon, 8.64 grams of hydrogen, and 17.3 grams of nitrogen. So this adds up to about 100% within experimental error. And then what we're going to do is we're going to convert it to moles, because atom and mole ratio is the same thing. And so to convert it to moles, we're going to do this. We're going to multiply carbon. For every mole of carbon atoms, it's going to weigh 12.01 grams. Just right off the periodic table. So this is the molar mass of carbon. For hydrogen, I'm going to use this. For every mole of hydrogen atom, 6.022 times 10 to the 23rd hydrogen atoms, it's going to weigh 1.008 grams. And then for every mole of nitrogen, 1 mole of nitrogen weighs 14.01 grams. Nitrogen. I could have done it by U, assume 100 U sample, but we'll just do it by gram. And so what do I get? Well, 74.1 divided by 12.01 gives me 74.01 divided by 12.01. Actually, I'm going to stop here. So we get it to moles, and then we have a mole ratio here. Actually, let me just finish this really quick. And so 74.1 divided by 12.01 gives me 6.16. 6.16, and I'm allowed 3, so I'm going to carry 1 extra. 6.169 moles of carbon. 8.64 divided by 1.008 gives me 8.571 moles of hydrogen. And 17.3 divided by 14.01 gives me 1.234 moles of nitrogen. And so now I have the mole ratio. Formula is just a mole ratio. So let's go ahead and write the formula for this out. The formula for this is going to be C 6.169 H 8.571 N 1.234. Now this is a mole ratio. It can't be an atom ratio because can we have a fraction of an atom? No. And so to make it qualify both as an atom ratio or a mole ratio, we need to get it into the simplest whole number ratio. So what we're going to do is we're going to divide by the smallest number. That should hopefully get us whole numbers here. And so we're going to go C 6.169 divided by 1.234, which is the smallest. H 8.571 divided by 1.234, and then N 1.234 divided by 1.234. And so let's do the first one. 6.169 divided by 1.234 equals 4.999. And so I get C 4.999. H, okay, it's going to be 8.571 divided by 1.234, 6.945. And then N will be 1.000. And so what we're going to do is we're going to get the simplest whole number ratio. So we're going to just round this. And so this is going to be C5H7N. This simplest whole number ratio just tells me for every 5 carbons, I'll have 7 hydrogens and 1 nitrogen. And this is called the empirical formula. Okay, there's another step here, and the other step is sometimes we stop here. We stop here if it's a lattice type structure. A lattice type structure, but if it's a molecular structure, we continue. I think that this is a molecular structure because it's all nonmetals, so most likely it forms molecules. And so let me talk about that next time, since we need to do some lab today. And so what is the lab that we're going to do today? We'll start. We're actually going to continue these labs, so I think in the next one we'll look at it too. But we're looking for evidence of chemical reactions. What are the types of things that we look for as far as evidence of reaction goes? Yeah, precipitate, heat, light, those types of things. These are all the things in Chapter 8 here. So we'll take a look quickly. All right, this cloudy cloud formation here, that's what we call flocculent precipitate. And there's evidence of change because we're taking two, what we call CCSs. This is a clear colorless solution, and in the dropper there's clear colorless solution, CCS, and then we get a solid form. That solid is not that low. It could be a heavy solid which sinks right to the bottom. Eventually that solid will sink to the bottom, but the crystals are quite small. In the middle we have effervescence, or generation of a gas. Here we have CCS and a white solid, and we're generating a CCG. CCG is clear colorless gas. Here we have some heat and light being evolved. Here we have some light. Sometimes the light is not a chemical process. Sometimes that light is a physical process. In these things, these little glow sticks, it's a chemical. But in other things, like a light bulb, it's a physical process. Here we have a cold pack. Hot and cold packs are a chemical process. You can feel the heat. And so what are the reactions we're looking at today? The reactions we're looking at today are here. So we're going to mix. We're going to mix hydrochloric acid, HCl, with sodium carbonate. Well, the first thing I think about is metathesis. The first thing I think about is metathesis because we're mixing together cations and anions. And then what we're going to do is we're going to look for favorable ion combinations here to see if there's a reaction that occurs. And so today we're just going to take observations. Do you see any evidence for a reaction occurring or not? And so when we mix these, what you're going to do is you don't have to be very careful about the amounts. All the chemicals there are in beakers. And in the beakers there's a plastic pipette. 1 squirt of the plastic pipette gives you about 1 milliliter. And that's probably all you need, is about 1 squirt. And so what we do is this. We put in the sodium carbonate into the test tube here, about 1 squirt. And then we add the HCl slowly, because there's a sequence to this. Have you ever heard the safety rule AA? Add acids. We always add acids. That way we can control something. Sometimes a lot of heat's generated, sometimes the reaction is quite vigorous. So we want to add the acids slowly, drop by drop, to see. If the reaction is kind of violent, go even slower. If nothing much is happening, you can add it a little quicker. But we're going to add another pipette full. Those are plastic pipettes back there. And then observe this. When you mix it, you can either rotate it like this, or you can hit it like this to get it to mix. You want it to mix thoroughly. You don't want to use your stir rod. If you use your stir rod, you have to clean it each time, which takes too much time. And so just try to mix it like this. Okay? And then just observe what happens. When you observe what happens, here's some vocab that you could be aware of. And their abbreviations. Precipitate is usually abbreviated PPT. Flocculent precipitate, which is that kind of that cottony precipitate that we saw earlier, is FLOC. Milky precipitate is if the whole thing fills with white precipitate and it looks like milk. You can't see through it. We call it milky. Cream, CRM. Clear colorless solution, CCS. Heavy precipitate will sink immediately. Clear means you can see through it, but you need a color as well. These are the colors down here, red, orange, etc. Just because something's clear, that doesn't mean it's colorless. If it is colorless, then make sure you just say colorless. Opaque. Clear colorless gas is CCG, which is CO2. Smoke, effervescence. Effervescence is that bubbling. Solution, SOLN, gelatinous, GEL. Gelatinous is a precipitate that looks like jello or gelatin. All right, any questions on this? You can work with a partner on this, and then what we'll do is we're just going to put 1 reagent in the test tube, and if there's a choice, add the acid. And so what I do on the first one is I put 1 squirt of sodium carbonate in here, then walk over to the HCl, and then start dripping the HCl slowly until you get 1. And then observe. Okay, that's going to mean there's going to be a backup for everybody that needs HCl. So in order to prevent much backup from occurring, you can go in any order here, except for some of these. Like for example, test tubes 6 through 10, you're going to need for reactions 11 through 15, and so you can't do that. there. To keep track of the test tubes, we have Sharpies. You can just write the number on the test tube itself. I only have 3 Sharpies, so you got to share them. For reactions 16 through 19, it asks you to add phenolphthalein, which is a dye. We're going to skip that phenolphthalein. All right, so go ahead and mix these together and see what you get. You're going to need goggles since we're doing these chemical reactions. And these are all metathesis reactions. We're looking for favorable ion combinations. What ions like each other? Did anybody forget their goggles? Yeah. All right, I have some extras. Some loaner.
You didn't like there was like.
Yeah, goggles are required for this. Also, if you have any food or drink, make sure you consume it before we start the lab or put it away.
So we only need one set.
Oh yeah, I have some. Yeah.
That was one.
No, she wants to label the. Oh, the label.
Do you label the black or we just label
We're gonna be at Cody. Well, you can just. Yeah, no one. Oh, yeah, he's so
first one you guys do yeah, no, So we're starting off by doing the base first, which is the bottom, and then adding in acid, which is the top. Do this one at a time, or do you just want to
Yeah, okay. Oh, here's the shirt.
Oh, wait, that's not right. We are done. We dump it in here. We dump it in here when we're done. We just hold this, hold on to it. Chemical?
1 through 5 you can dump in waste, or actually those can go down the sink
Can I
too.
drink it or?
No, don't drink it.
All right, make sure you guys have your safety goggles. You throw it in the waste jug over there.
So everything acid or everything that's acid is like so that's why we're write that down right now. because I think the effect will disappear over time.
So I should not write.
Yeah, well, there's a definition for just right what you see right now, and we'll figure out the actual terms later. This one is number 4. I'll be relying on the detail on this one. Diego. Everyone, what's up? Very good. I promise there's nothing. I promise nothing. Don't jinx it. Alright, that's it for right now. On to the next. This is an experience. That was me. That was not me at all.
Nah, she gonna start tripping like this. I'm gonna see you outside. For now, the auto creates this one.
This is
It's on the other page. Just put them in the water.
White. Yeah. Everything was out.
There's a before and after, right?
Yeah. Well, during the during the action and after the action.
Two people in here at the same time so you can see the look. Who did it? We'll just make sure the light is right on it for the car. All of you guys are like busy. If this is right. Sorry, you know what that is? It's down. It was you know what EMS is?
Which one actually is?
But I forget ammonium
Very important, very important. Very important.
Oh, check that out. There was something falling at the bottom. You see
Just gonna sit
Oh man, I thought I'd have a break in a second. HCl.
What was 7? Did you do 7 yet?
White. Alright.
It had a PG?
Two is,
Or was it over there?
I think, I don't remember. I honestly don't remember.
Oh, yeah.
This moment, yeah. So we did all of this, now we're kind of,
Like the first 10 were like basically like 5 to like 10. They were like white, right?
yeah. Yeah. Oh, you guys didn't have one?
Yeah, those are, I was happy.
Okay.
All of ours were just plain heating.
So effervescence. Okay, so then that's not, yeah, see, which is, in some of them, like, that one, you see how that's kind of like gelatinous?
It's changing.
Yes, that's why I was like,
Well,
bring it back here.
first,
You can look at it.
there was a period where it was like solid at the bottom.
Same, look at this.
Well, that's why.
Look at how, yeah, this is ammonium carbonate, and then, what is that, RM, chloride?
Very
Yeah.
similar,
Properties, right? It's given off the white precipitate, but it depends on what it's mixing with, because when it mixed with sodium, when it mixes, yeah, the sodium carbonate, it's making more until that base kind of you see that? So it depends on what the acid is and the base, because all the bases is what you put in first, it'll be just keep the acid.
So for numbers 1 through 5, we're not going to be ones that we have
That's potassium carbonate. It's like a planet. He said those were the ones that we couldn't do out of the wall. That's why I was like, all right, let me just do that. That's okay. As long as they're all right. Okay. So now we know. And also, what's the second part?
keep going back.
So you see how